Usually, when talking about oscillators, the first thing that may come to your mind is crystal oscillators that feed microcontrollers with clock. And when looking at a crystal oscillator, you will see a number that makes it special, which is the waveform frequency that it can generate. Today in this video, we will build an astable multivibrator circuit using transistors, discuss the working principle of it, and we will even take this oscillator to the next level and build an electronic bagpipe. We are going to listen to different levels of frequency today, so get ready and let's start our video. Now to understand the working principle of this astable multivibrator oscillator circuit, let's have a look at its circuit diagram. At the first look, we can say that this is nothing but an SR latch. So to have better understanding, let's see how this latch circuit works. When connecting this circuit to a power source, definitely one of these transistors will conduct. So let's assume that the transistor on the left hand side will conduct first. In this case, the output Q will have logic 1, while the output Q complement will have just the opposite logic signal, which is logic 0. This happens because while this transistor is conducting, the terminal Q complement is shorted to ground. In the meanwhile, the other transistor will be derived to ground, so it will be turned off. That's why at the output Q, we will have around 5 volts, which will light up the parallel LED. Remember that the left-hand side transistor base current flows through this branch, so if you had a series LED in this branch, it will light up slightly. When pressing on the reset button, the left-hand side transistor will be derived to ground. So at this point, the terminal Q complement will have logic 1 because in this branch, the right-hand side transistor base current will flow, which is relatively small, so it won't cause a significant voltage drop at this resistor and around 5 volt can be observed at Q complement terminal, which will turn on the right hand side transistor, shorting this LED so we have logic 0 at the output Q. Of course, this LED will light up for logic state indication. Pressing on the set button will return us to the first state, where we have logic 1 at Q terminal and the opposite at Q complement terminal. Remember that at this point, pressing again on the set button will do nothing, because the right hand side transistor is already derived to ground. As a final note, I noticed that many people on the internet consider this circuit as a flip-flop, but it's not, because a flip-flop has a clock input feeding it, while latch circuit doesn't. Alright, we are done with the theory now. So for the sake of demonstration, let's build up this circuit on a breadboard and see how it will perform. You may wonder why would I connect an oscilloscope to such a circuit, right? Obviously, with such a setup, we could get rid of switch bouncing by transforming a mechanical switch to electrical switch. That's why the transactions between voltage levels are perfect. To learn more about switch bouncing, you can watch switch bouncing and debouncing circuit episode from the card shown above. Before diving into the concepts behind this circuit, let's agree on the fact that capacitors are considered as open circuit while they are fully charged and short circuit when they are fully discharged. To show you this in practice, I conducted a simple experiment where I set the voltmeter on continuity test and connected its probes to the capacitor leads after flipping it. You will notice that the multimeter is giving a beep sound at the instant a contact is constructed, indicating for a short circuit, because the capacitor is fully discharged. But after a very short amount of time, the sound disappears, indicating for an open circuit, because at this time the capacitor is charged for the same level that the multimeter is supplying for conducting the continuity test. Okay, now it's time to make things a little bit harder by moving to this astable multivibrator oscillator circuit. which works similarly to SR latch. But here, we don't have input signals, set and reset. So this time, just like we did with the SR latch, let's assume that the left-hand side transistor is turned on. Because anyways, when connecting this circuit to a power source, one of these transistors will be turned on. So at this point, we have the following outputs. Okay, now this capacitor will start charging until it reaches the right-hand side transistor on voltage, which is typically 0.7 volt. Now let the game begin. When the right-hand side transistor is turned on, the terminal Q is shorted to ground. At this instant, the left-hand side transistor will be derived to ground, leading it to be turned off. Now this capacitor will start charging until it reaches the forward biasing voltage of this transistor, which will turn it on, and the other transistor will be derived to ground, leading it to be turned off. In this way, you will have two infinitely alternating outputs. Remember that the oscillator switching frequency depends on these components due to the RC time constant. Keeping both circuit sides symmetrical will give you a signal with 50% duty cycle, and any imbalance in the circuit will change that. In my test, I selected 1 microfarad for both capacitors and I could get a frequency close to 300 Hz. The problem of the output right now is that it's not a square wave, which is not desired at all. So as a quick solution, I added two NPN transistors to the circuit output so that the charging and discharging of the capacitors doesn't appear at the output. I also lowered the capacitor's value to 0.1 microfarad to get higher switching frequency. Adding parallel LEDs to the output transistors and lowering the switching frequency will flicker the LEDs continuously. Finally, we have reached the monster level. Alright, that was scary, but hold on. We have already covered everything related to this circuit, so no need to get scared, because the only extra thing we have here is a voltage divider and a potentiometer. The main idea behind this construction is to cause an imbalance to the circuit and to change the capacitor charging voltage to modify the output frequency when pressing on one of these buttons. In this circuit normal state, the oscillator doesn't work because the right-hand side transistor base is not connected to the power source. Now let me tell you how it works. For example, when pressing on this button, a voltage of 2.25 volt will be formed across this resistor, and pressing on this button will form 4.5 volt across the same resistor due to the voltage divider. This change in the capacitor supplying voltage will lead to form different levels of frequency at the output, which means different sound. For demonstration, I constructed this circuit on a breadboard and let's see how it will work. This potentiometer is used for sound adjustment. Now it's time to make this circuit permanent so I can play annoying music when I want. If you used to sit down and deal with electronics on your workbench, then definitely you are familiar with burning smells and smoke coming out of your breadboard, which is a big indication of that there is something going wrong, right? Well, definitely none of us creates short circuit on purpose, and they happen accidentally. So, is there a way of avoiding short circuits? In this video, I want to share with you two short circuit protection circuitries that I found online, explain their working principle, and compare between them. We have a lot to cover today, so what are we waiting for? Without any delay, let's start our video. As a warm-up, let's start with the relay-based short circuit protection circuitry. From the circuit diagram shown, as long as there is potential difference supplied at the input terminal, the red LED that's connected to the normally closed terminal of the relay will be turned on, indicating that the output is disconnected. When pressing on the push button, which connects the input to the output terminal of the circuit, obviously the input voltage will be the same as the output voltage. But hold on, you haven't seen the magic yet. Since the output terminal is connected to the relay coil through a diode, this means that once we have potential difference at the output, the relay coil will be energized, leading the relay switch to change its state, so the connection is established between the common and normally open terminals. With that being occurred, now we have physical connection between the input and the output of the circuit. Of course, the green LED will light up indicating that we have potential difference at the output terminal. But what about the remaining circuit components? First of all, we have this series diode, which will isolate the relay coil from the circuit output terminal. This shunt diode, on the other hand, is a freewheeling diode. The way it works is explained in details in Make Your Own Relay Driver episode, so make sure that you watch that video if you don't know what freewheeling diode does. Finally, this shunt capacitor is a bypass capacitor used for stabilizing the voltage across the relay coil. Okay, so how can this circuit protect me from short circuits, right? When a short circuit occurs, what happens is that the electrical current will definitely select the path with lower resistance, shorting this whole part, which will lead to de-energize the relay coil, and the relay switch will return to its normal state. So, the physical connection between the input and the output will be lost, and the red LED will light up back again. After understanding the working principle of this circuit, let's see how it works in practice. I built up the relay-based short circuit protection circuitry on a breadboard and tested its functionality, and here's the result. I hope that you liked this video. Thank you for watching and whoa man, hold on. We still have one complete circuit to talk about, right guys? We haven't forgotten. Okay, that's fine, no problem. The last thing I want to mention about the relay-based short circuit protection circuitry is that both the red LED and the green LED share the same current limiting resistor, which I think is a nice idea, since anyways they don't work together at the same time. Now let's move on to this transistor-based short circuit protection circuitry and see how it works. When applying potential difference to the input terminal of this circuit at its initial state, a potential difference will be formed at this node, since in microseconds of time, electrical current will flow from the input terminal to ground, taking this path. And as long as there is enough voltage at the circuit output terminal, the NPN transistor will be turned on, deriving the PNP transistor to ground, which will turn it on as well. This will establish a direct connection between the input and the output through the NPN transistor, shorting the red LED and lighting up the green LED as an indicator. And here's what happens when a short circuit occurs at the output. Of course, in such a case, the potential difference at the output will be zero, which will turn off the NPN transistor. On the other hand, the PNP transistor won't be derived to ground anymore, so it will be turned off as well. In this case, the electrical current will take the following path. Since this branch is not shorted anymore, so the red LED will light up indicating that the output is disconnected. And guess what? When the short circuit is removed, the transistor-based protection circuitry will automatically reconnect the input to the output, since once again a potential difference will be formed at the output, and the process will loop back again. After understanding the theory part, let's do something fun. I constructed the transistor-based short circuit protection circuitry and tested its operation modes, and here's the result. After building the relay-based short circuit protection circuitry on a breadboard, I've conducted a simple experiment to see the features of each topology to compare between them. The important parameters for doing such a comparison are voltage drop at the output, the current drawn by circuit in no load condition, and input-output isolation for safety. From the obtained results, we can see that the relay-based circuit consumes a relatively large current, even in no load condition, due to the parallel relay coil. But the good thing about this circuit is that it provides isolation to your power source, which serves safety purpose. Now it's time to see how these circuits operate in action. So I used a buzzer as a load and tested both circuits. Relay drivers make dealing with relays an easy job, especially when using them with microcontrollers. So, I thought the best way of learning their working principle is making one with a different design. In this video, I will show you the steps I went through while making a relay driver and some important concepts that may help you in your electronics project. So, without any delay, let's start our video. Relay is a controlled mechanical switch that provides isolation to your circuit. And to control it safely with a microcontroller, it is recommended to be used with a driving circuit. But before anything, let's take a look at the working principle of relays. This is the internal circuit of a relay. So, when energizing its coil, you will hear a sound, meaning that the switch has moved from normally closed to normally opened pin. Boom, that's it. After having an idea about relays, let's have a look at its deriving circuit. As you may have noticed from this circuit diagram, when applying logic 0 to active low node, the gate of the PNP transistor will be derived to ground, leading it to be turned on, allowing the current to pass from its emitter to its collector, which will energize the relay coil and turn on the red LED. On the other hand, when applying logic 1 to active high node, the NPN transistor will be activated, which will drive the PNP transistor gate to ground. This will turn it on. So, this will do exactly what applying logic 0 to active low node does. Well, obviously, when the relay switch is on, the green LED will light up, indicating that the relay switch state has changed. But wait a second, what's the purpose of this shunt diode then? This is actually called freewheeling diode, and its purpose is to provide a discharging path for the relay coil to discharge its energy when the voltage potential across it is removed. This procedure works as follows. When the potential across the relay coil is removed, the coil itself stores its energy for a time, since the current in the coil doesn't change instantaneously. Instead, it decreases with an exponential decay, like the graph shown. And from the inductor voltage formula, the voltage is equal to the inductance times the current change rate. This will give us a negative voltage, since the current amplitude is decreasing. So, this will form a reversed voltage across the relay coil when de-energizing it, which will harm other components in the circuit. So, adding a parallel diode to the coil will remove this reverse voltage. This technique is very common and you may have seen it in other circuits. Having completed the theoretical part, let's do something practical. Here I have constructed the circuit I have discussed to test the functionality of active low and active high feature of the driver. After that, I've used STM32 microcontroller to control the relay driver by generating an interrupt that changes B9 GPIO pin state when a falling edge at B5 pin is detected. And here's the result. This is actually a way of turning push button into on-off switch. And here is the circuitry I have used to make triggering falling edge interrupt work properly. But what is the purpose of this shunt capacitor for such a simple circuit? Well, this will be the topic of my next video, so make sure that you smash the subscribe button even before finishing watching this video. Before putting everything together on a breadboard, I decided to change the place of the red LED so that it indicates that the driver is connected to a power source. Well, usually relays are used to control AC operating devices, but I didn't do this in my video since the purpose of my video is educational. To make this project permanent, I soldered the required components on a breadboard to make use of it later on. But remember to glue the connection side of the board after making sure that it's working properly to avoid unwanted short circuits in the future. As a final test, I mounted a buzzer on the output terminal of the board and tested both active low and active high pins to check if everything is okay. And here is the result. As we have seen previously, we were able to build oscillators using transistors and relays. In this video, we are gonna use an amplifier as a comparator to design an oscillator that oscillates at a frequency that we determine. We are gonna design some cool stuff today, so get ready and let's start our video. In order to understand the working principle of the Opamp based oscillator circuit, we need to know how comparators work. Luckily, in comparators, we only have two cases to understand. In the first case, the non-inverting input voltage is higher than the inverting input voltage. This will lead the output voltage to be pulled to V+. In the other case, on the other hand, the non-inverting input voltage is smaller than the inverting input voltage, which will lead the output voltage to be pulled down to V-. And that's all about comparators. Having understood the working principle of comparator, let's make it oscillate. For this Opamp based oscillator circuit, I have used LM358 Opamp, but you can use any Opamp that you have on your workbench, because the only thing that you should care about when choosing an Opamp for this circuit design is the unity gain bandwidth, because it what determines the switching frequency limit. Now it's time to understand how this oscillator works. At the first look at this circuit, we can notice that the non-inverting input of the op-amp is connected to a voltage divider, and the inverting input is connected to a capacitor. At the initial state, the capacitor is discharged, so the voltage at the inverting input is 0, while the voltage at the non-inverting input is 2.5 volt due to the voltage divider. And from the comparator rule, since the non-inverting input voltage is higher than the inverting input voltage, the output will be pulled to 5 volt, which will turn on the LED. Now guess what will happen? Since these two resistors are pulled up to 5 volt, they are now connected in parallel. So now the voltage divider circuit will be like this. And since the pull-up equivalent resistance has changed, the non-inverting input voltage will be changed to be 3.3 volt. So now the capacitor will start charging trying to reach 5 volt, but hold on, the comparator won't allow it, because at the instant the capacitor voltage exceeds 3.3 volt, the comparator output voltage will be pulled to ground, and the LED will be turned off. Now these two resistors are connected in parallel, so the voltage divider circuit will be changed again, and here it is. As you can see, the pull-down equivalent resistance has changed, which will lead the non-inverting input voltage to be changed again, to be 1.62. Alright, so right now, as long as we have 0 voltage at the output, the capacitor will be discharging, trying to reach 0 volt. But the comparator will not allow it, because at the instant the capacitor voltage reaches 1.62 volt, the comparator output will be pulled up to 5 volt, turning on the LED. This will change the voltage divider circuit and the non-inverting input voltage will return to 3.3 volt. In this way, while the capacitor voltage is oscillating between 1.6 and 3.3 volt, the oscillator output is oscillating between 0 and 5 volt. Alright, so how can we determine the output switching frequency? Well, since the oscillator depends on this RC circuit, we can approximate the output switching frequency using the time constant formula. For the sake of demonstration, I've chosen 10 kilo ohm and 10 microfarad for RC network. And by applying the formula, I should be getting something around 7 Hz. Okay, now it's time to see how this oscillator circuit will perform. Of course, you can achieve higher frequency by lowering the values in the RC network. In my previous video, I had no problem with my microcontroller generating an interrupt when a falling edge is detected, which is nothing but pressing on a push button. Of course, this was not the case in my first trial. So what's happening over there? And how could I fix this problem? To answer these questions, without any delay, let's start our video. As I had promised, in this video, I will be talking about the circuit I used for triggering falling edge event by the microcontroller. Although it seems simple, let's see what the theory tells us. When connecting this circuit to a GPIO pin of a microcontroller, the controller will read 1 as long as the push button is at its normal state. Once the push button is pressed, the GPIO pin will be shorted to ground, so the microcontroller will read logic 0. Of course, using a relatively large pull-up resistor is a wise choice, since while the push button is pressed, the current will flow directly from the power source to ground through the pull-up resistor. So, as Ohm's law tells us, as the resistance increases, the current flowing through it will decrease. Unfortunately, there's nothing perfect in this world, so let's hook up the oscilloscope probes and see what's happening in reality. For the time being, let's remove this shunt capacitor and see what happens on the oscilloscope screen when pressing on the push button. This explains the misbehavior of the relay driver circuit when the shunt capacitor was not connected, since in this case, the microcontroller will detect multiple falling edge events at one shot. And of course, this is not desired. The mistake I have done is that I considered the push button as a perfect switch, but it's not, since the connection is not established at the moment I press on the button. But the button internal metallic structure takes a bit of time to come to a stable state and does what it's supposed to do. This phenomenon is called bouncing effect. So how could the capacitor solve the problem? Well, we all know that there are evil spirits and magical force hidden right in between the plates of the... That was pure bullshit, okay? What the capacitor actually does is that it slows down the voltage level transaction speed, since the voltage doesn't go to zero instantaneously across the capacitor. Now, let's connect the capacitor parallel to the push button and observe the oscilloscope screen. As we have seen, now the circuit output is stable, so it can be connected to a microcontroller GPIO pin. This method is called switch debouncing. Beside the hardware solution, there is also a software solution, and it has several algorithms that can be implemented. One way is to wait after the interrupt occurrence for at most 10 milliseconds, since there can't be a creature on this planet that can press a button at this short time. In my previous video, we were able to use an Opamp as an oscillator. So how about converting this square wave to a triangular waveform using an amplifier again? In this video, we are going to discuss the working principle of integrators. And next week, we will see how low-pass filters and high-pass filters affect the signal properties. We're gonna play with signal shapes today, so get ready and let's start our video. At the first look at this circuit diagram, the first thing that may come to our mind is differential amplifiers. But here, instead of feedback resistor, we have a capacitor, and it's behind the integration functionality of the circuit. So to have a better understanding, let's have a closer look. To make analyzing this circuit easier, we need to do two assumptions. First, the voltage at the non-inverting input is equal to the voltage at the inverting input. Second, the current at these terminals is equal to zero. By knowing this, we can use Kirchhoff's law to equate the input current to the feedback current, which is nothing but the capacitor current. Of course, we know that the input current is equal to the input voltage divided by R1, and the feedback current is equal to the capacitance times the derivative of the output voltage. And by doing a little bit of math, we can see that the output voltage is equal to something times the integration of the input voltage. Boom! That's why this circuit is called voltage integrator. But hold on, what is this something then? Well, to make things clear, it's better to analyze this circuit in frequency domain instead of time domain. All we need to do is to use the feedback capacitor reactance, and using the same procedure, we can get the ratio V out to V in, which will form the op-amp gain. From the gain formula, it's obvious that this circuit acts as low-pass filter, because when supplying a signal with a very high frequency, the gain will be very low so that the signal will be eliminated at the output. On the other hand, when supplying DC voltage at the input, this will lead the gain to be infinity, and this is not possible of course, because the output voltage is limited between VCC and minus VCC, which is called saturation mode. So we can imagine the frequency response of this circuit to be like this. In order to avoid going to saturation mode in low frequencies, it's possible to add parallel feedback resistor to the feedback capacitor. In this way, the amplifier will work as the integrator in high frequencies and differential amplifier at low frequencies. After this modification, the frequency response graph will be like this. These parameters are important for Opamp circuit design because in order to let this operational amplifier work in integrator mode, the input signal frequency must be higher than FL. Notice that any input signal frequency higher than F0 won't appear at the output, so make sure that your input signal frequency falls between FL and F0. As a practical example, I've chosen the following parameters for my design and constructed this circuit on a breadboard, and used a 5-5 timer to generate a square wave signal with a frequency close to 8 kHz. After feeding the square wave signal to the integrator circuit, we can see practically how the square wave signal has been converted to a triangular waveform, with a decrement in the signal amplitude. Filters plays a big role in electronics world, where signal filtering is needed, since by using a high-pass filter, it's possible to convert this signal to this signal by removing its DC content. It's also possible to convert a square wave signal to a sine wave signal by using a low-pass filter. In this video, we are going to discuss the basics of filters and the steps of RC filter design. We are going to play with signals today, so get ready and let's start our video. Now let's have a look at the working principle of high-pass filters before jumping into its application. All what we need is to find the relationship between the input voltage and the output voltage, and this is possible by applying the voltage division formula. Of course, we need to remember the capacitor reactance and the impedance formulas. And here you go. Now we have the output voltage amplitude formula in terms of the input voltage. Now to see the beauty of this simple circuit, let's apply DC voltage at the input. And as we know, DC voltage has zero frequency. And by applying this to the output voltage amplitude formula, this term will go to infinity, which will lead the output voltage to go to zero. This means that this circuit blocks DC voltage. Now to show you a practical example, I've used a 5-5 timer to generate a square wave signal with a frequency of 8 kHz and fed it to a high-pass filter. What makes this signal an AC signal is that its average voltage is zero. This means the positive part of this signal is equal to the negative part of it, which was not the case in the input signal. So what values of R and C should we choose for this circuit design? Well, to have a better understanding, let's draw the frequency response of this circuit. So assume that we are feeding this circuit with a signal that has a very high frequency, and according to this formula, this term will be so small that it can be ignored, and these two parameters can be cancelled out. So what's remaining is that the output voltage amplitude is equal to the input voltage amplitude. Alright, so now we can draw the frequency response of the high-pass filter. And remember that the cutoff frequency can be determined using this formula. The cutoff frequency is where the filter gain is equal to minus 3 dB, and minus 3 dB is where the signal output power is equal to half the input signal power. So make sure that your signal frequency is higher than the cutoff frequency. For my design, I've chosen 1 kilo ohm and 10 microfarad for R and C, which gives me a cutoff frequency of 16 Hz, which is way lower than my signal frequency. Alright, so now it's time to move on to low-pass filters, which will be a piece of cake for us, because we have covered all what we need. Alright, so like we have done previously, we need to find the relationship between the input voltage and the output voltage using the voltage division formula. After that, we determine the filter behavior at low frequencies and high frequencies to be able to draw the frequency response of it. Let's start by applying DC voltage at the input, which has zero frequency, and by applying the output voltage amplitude formula. These two parameters will go to infinity, and large numbers will cancel out, so we can see that the output voltage amplitude is equal to the input voltage amplitude. On the other hand, by applying a signal with a very high frequency at the input, we can see that this term goes to zero, which will lead the output voltage to go to zero as well. Okay, so now it's possible to draw the frequency response of this filter, and here it is. The cutoff frequency can be determined the same way as previous. Low-pass filters can be used in power supplies with rectifiers, and they are also used in noise removal and harmonics filtering. Low-pass filters are also used in the bouncing circuit. For more details, you can watch switch bouncing effect and the bouncing circuit episode. For the sake of demonstration, I've combined a high-pass filter with cascaded low-pass filters to form a band-pass filter. But hold on, what would a low-pass filter do to a square wave signal? And why would I build a cascaded low-pass filter network? Well, let me tell you by answering the first question first. A square wave signal is actually composed of many sine waves, and they are called harmonics. Each harmonic has its own amplitude and frequency, and the harmonic amplitude decreases as the harmonic order increase. So higher order harmonics has less effect in forming the square wave signal. There's also one more thing to notice, and that is the harmonic frequency increases as the harmonic order increase. So a low pass filter will allow me to cancel all the harmonics except the first order harmonic, which has the same frequency as the input square wave signal. That's why a sine wave signal appears at the output when feeding a square wave signal to the filter. One final note related to harmonics I want to mention is that using input signal with a higher frequency makes it easier to filter because in high frequency square wave signals, the frequency range between harmonics orders becomes larger. Alright, so what's the reason behind using cascaded low pass filter then? The advantage of using cascaded filter is that it makes it more accurate when selecting a specific frequency. That's why it was possible to select the first order harmonic only and reject the other harmonics, so we could obtain a sine wave shape. When it comes to cascaded filters, calculating the cutoff frequency is different, and it's done by using this formula. So according to my low-pass filter design, first I found the cutoff frequency of one low-pass filter. After that, I've used this value to find the cutoff frequency of the third order low-pass filter. The whole function of this bandpass filter is that it removes the DC offset from the input square wave signal and converts it to a sine wave. As a quick note, this is not the perfect way of cascading filters, and I've done it this way only for demonstration purpose. Using an on-off switch is quite convenient to turn on/off your load, but this might be an overkill if your load is a couple of LEDs or just a buzzer. Unfortunately, using a push button on its own doesn't seem a cheap replacement for the on-off switch. However, there is a trick that we can use to solve this problem with the help of 555 timer. In this video, we are going to have a look at this 555 timer based latch circuit, explain its working principle, and test its power consumption when it's used to convert a push button into an on-off switch. We have a lot to cover today, so what are we waiting for? Get ready and let's start our video. Now let's carry on. In order to make a push button act as an on-off switch, we need something that stores the state of the switch and switches polarity once a push button is pressed. In this case, the first thing that may come to your mind is Latch Circuit, which exists in 555 timer IC. From the circuit diagram shown, when a potential difference is applied to the circuit while the button is not pressed, half the applied voltage will appear at this node due to the voltage divider. And the series 5 kilo ohm resistors of the 555 timer will divide the applied voltage at these nodes to 2 VCC over 3 and VCC over 3. After having the input voltage of these comparators, we can predict their behavior. Note that the working principle of comparators is explained in Opamp based Ocillator episode. For more details, please follow the link in the card over here. Alright, now let's move on. According to the comparator's inputs, both comparators will output logic 0, so we will have both set and reset are zeros, which will lead Q bar to be logic 1. And the output is inverted, so we have logic 0 at the output. Now let the game begin. When the push button is pressed, the capacitor will start charging, and at that instant, the voltage at this node will drop to 0. Now let's see how the comparators will react to this change. This comparator will give us logic 0, and the other one will give us logic 1. So the values of S and R are as follows. This will lead Q bar to be 0 and the output will be 1. At this state, if the push button is kept pressed, the capacitor will be charged to 2.5 volt, which is the voltage of this node. So now, the values of S and R are both the values of S and R are both zeros, just like the previous state. But now the latch will keep its value, which is logic 1, because the reset hasn't been triggered yet. Of course, releasing the push button doesn't have any effect on the latch state. So, the state is kept as long as there is no change occurs to the circuit. Now notice that the capacitor is charged from the 555 timer output, which is theoretically 5 volt. Now when pressing on the push button again, the capacitor will be discharged through this path, raising the voltage at this node to be 5 volt for a very short amount of time. At this instant, the comparator's outputs are going to be logic 1 and logic 0, which means that the latch reset will be triggered, changing the latch value from logic 1 to logic 0. Q bar will be logic 1 and the inverted output will be logic 0. So we could return to our initial state. One last note is that make sure to choose a low capacitor value to ensure fast response. Alright, now it's time to put everything on a breadboard and test the circuit with some different loads. I just want to mention that I've tried to run a motor using this circuit, but none of my trials were successful. We can see that when the circuit output is 0, the current consumption is around 2.3 milliamps. Building an oscillator out of a relay seems an interesting idea, since with such a circuit on your workbench, you can do a lot of cool things, like flickering LEDs, testing buzzers, or even stepping up DC voltage. In this video, I want to share with you this relay-based oscillator, explain its working principle, and how to use it in a boost converter to step up DC voltage. We're gonna deal with noisy relays today, so get ready and let's start our video. Now let's begin with revealing the secret behind this relay-based oscillator. When energizing the relay coil while the relay is at its normal state, the electrical current in this circuit will take this path, leading the relay switch to change its state. Now guess what will happen? As you may have noticed, now the circuit is not connected to ground anymore. This will lead the relay switch to return to its normal state when the relay coil loses its energy. But this is not the end yet, since now the circuit is connected to ground, which means that the relay will be energized and the relay switch will change its state again. This process will go on forever as long as there is potential difference across the relay coil. But hold on, there's something wrong in this circuit design, right? Well, if you used to watch my videos, you will notice that there is missing diode parallel to the relay coil. Yes, of course it's the freewheeling diode. Now let me show you the importance of this component. So I've just constructed the same circuit with and without a freewheeling diode on a breadboard and connected the oscilloscope probes across these terminals. Now let's see the difference in performance. Obviously, the freewheeling diode managed to remove the unwanted voltage spikes from the output and made the oscillator output signal more close to a square wave. But it's not perfect due to these pulses. So what's the reason behind their formation? Well, this topic is well explained in switch bouncing effect and the bouncing circuit episode. So make sure that you watch that video if you want to learn more about this phenomenon and how to deal with it. There's one more trick to talk about. Connecting a parallel capacitor to the relay coil will slow down the relay switching frequency, because now the relay coil will take more time to be energized, since during this time the capacitor is getting charged as well. So as an experiment, I will be connecting different capacitor values parallel to the relay coil to change its switching frequency, and let's see what will happen. We have seen that as the parallel capacitor capacitance increased, the relay switching frequency decreased. Now it's time to put this oscillator in action and test it with different loads. After understanding the working principle of relay-based oscillator, you may ask, how can this circuit step up DC voltage? Well, to answer this question, we need to understand the working principle of boost converter first. From the circuit diagram shown, while the relay switch is at its normal state, the voltage source will energize the relay coil, which will change the relay switch state. At this point, both the relay coil and the voltage source will supply the load, leading the output voltage to be higher than the input voltage. And since the relay coil is connected in series, the voltage across it won't be enough to keep the switch at normally opened position. So, it will return back to its normal state. And the whole process will loop back again. And here comes the role of other circuit components. The series diode will ensure that the current in the circuit will flow only in one direction, which is input to output. And the shunt capacitor will stabilize the voltage in order to have almost pure DC at the output. Now it's time to build this circuit on a breadboard and see how it works in action. As you have seen, we could obtain around 35 volt at the output from 5 volt input. So how could we reach that value? Well, of course it's not magic, but there is a formula used to calculate the theoretical value of the boost converter output, and it is derived from the inductor stored energy balance relationship. I won't be diving into theory right now, so you can stop the video here if you want to have a look at the formula derivation steps. Or if you guys are interested in this topic, I may do a complete separated video about boost converter. Let me know your feedback in the comment section below. In order to find out what the theory tells us about the boost converter output voltage, we have a missing parameter we need to find, which is the switching duty cycle. So to get this parameter, let's hook up the oscilloscope probes to the circuit and let's see what we can get. As we have seen, the duty cycle value was fluctuating between 12 and 14%. So I will consider 13 for my calculations. But wait a second, this is not the real duty cycle value. Because what we observed on the oscilloscope was the duty cycle during the discharge of the relay coil, but this is not what we need. Fixing this problem is quite easy. We just need to take out 13 out of 100 and this will give us the duty cycle according to T on time, while the inductor is getting charged. After obtaining all the necessary parameters, now we can apply the formula, which gives us a result that's very close to the real value. Unfortunately, this is not the way of building a boost converter because the system doesn't contain feedback loop, which means that the output is not regulated at all, and it will drop the instant a load is connected. Now let me show you what happens when connecting a load to the circuit. When searching on YouTube for voltage detector circuit, you will find many tutorials showing how to build the circuit and demonstrating it. But how and why it works? And is there only one way of building such a circuit? In this video, we will see together how this transistor-based voltage detector circuit works and why it can be used as a touch sensor. And we will even design a more reliable circuit using the concepts that we have covered so far. It's gonna be a good practice for everyone, so make sure that you watch the video until the end. We have a lot to cover today, so get ready and let's start our video. Alright, now let's focus on this transistor-based voltage detector circuit. At the first look, the circuit seems very simple, but why these NPN transistors are connected this way? Well, to understand this, let's find the total emitter current in Darlington pair transistor. First of all, we need to remember that the collector current is equal to beta times the base current, and the emitter current is the summation of the collector current and the base current. So overall, we see that the emitter current is nothing but the base current amplified. By focusing on the first transistor, these are the equations that we can derive, and if you notice, the emitter current of the first transistor is the base current of the second transistor, which is gonna help us to find the current parameters of the second transistor. And by applying the same rule for the second transistor, we can see that the emitter current of the second transistor is nothing but the first transistor emitter current amplified, which is the amplification of the base current. At the end of the day, we can summarize the working principle of the voltage detector circuit by the following statement. Whatever you have at the base is gonna be amplified at the emitter. So if we return to the transistor-based voltage detector circuit, we can see that the only difference is we have here one extra transistor stage, which is going to do nothing but increase the amplification factor at the output. Alright, so far so good. So how can this circuit detect the presence of AC voltage then? Well, actually the main idea is quite simple. When connecting an antenna or some copper sheet to this transistor base, it will act as a part of a capacitor. The live wire, on the other hand, will act as the other part of the capacitor, and the air between the copper sheet and the live wire is the dielectric material. And since the live wire and your body has reference to ground, this will allow a very tiny amount of current to jump through this capacitor to this transistor base, which is going to be amplified millions of times to appear at this transistor emitter. This will light up the LED indicating for AC voltage nearby. For the sake of testing this circuit, I built it up on a breadboard and used even 4 stages of NPN transistor. I also made up some sort of an antenna using a copper wire, connected it to the transistor base, and here's the result. Alright, so how can this circuit work as a touch sensor then? Well, here we have almost the same concept. While the antenna is acting as a part of a capacitor, your body will be acting as the other part of the capacitor, and the human body will pick up the electromagnetic field from the nearby main wire. That's why when touching an oscilloscope probe, you will see some signal with 50 Hz frequency. So touching the antenna with a bare hand will simulate getting this circuit close to a live wire, and the yellow LED will light up. But you know what? This circuit seems random and just amplifies everything. So what if I want to connect this circuit to a microcontroller to detect if there is main wire nearby or to use it as a touch sensor? Well, in order to have an improved version of this voltage detector circuit, the new circuit must feature both amplification and control. For this, I will be using amplifier for amplification and comparator to add control to the circuit. And to achieve this, I will go for LM358 integrated circuit, since it contains 2 amplifiers, which just fulfill my needs. Building a differential amplifier will provide amplification to the input signal coming from the antenna. I've chosen 10 mega ohms for the feedback resistance and 10 kilo ohms for the inverting input resistance, which will give me a gain of 1001. The non-inverting input resistance, on the other hand, is used for limiting the input offset current of the amplifier, the LED for indication, and that's it. I've built the circuit on a breadboard, tested its output using my oscilloscope, and it worked fine. As a note on the output signal, since the Opamp V- terminal is grounded, the signal is clipped at 0 volt. To make the comparison more clear, let's compare it with the input signal. To provide control to the voltage detector circuit, the amplifier output is connected to the non-inverting input of the comparator, and the inverting input is connected to a voltage divider to set the comparator at which voltage level it should trigger the output. By doing so, I have control over the circuit behavior. By the way, the working principle of comparator is explained in details in Opamp-based Ocillator episode, so make sure that you watch that video if you want to learn more about comparators. Alright, now let's carry on. I've chosen these resistor values for the voltage divider circuit to trigger the comparator once the amplifier output voltage is higher than the voltage divider output. At the end of the day, I built up the whole circuit on a breadboard, and here is how its output looks like. If you want to connect the comparator output to a GPIO pin of a microcontroller, it's possible to connect a low-pass filter to the comparator output. And here's how the signal looks like after connecting a low-pass filter. If you want to learn more about high-pass filter and low-pass filter design, you can watch RC filter design episode from the card shown above. Finally, here is how the circuit works in AC voltage detection. For test purposes, I've used the plate of a piezoelectric instead of the antenna, and it worked.